Hello everybody, welcome back to another Gregorious Maths video. I'm excited today to present the Rham cohomology. I haven't seen many videos on this on YouTube. I actually do know that Thematic has a video on this. But he doesn't go into many properties, so that's what I'll do here. In slightly concise fashion compared to the hour-long lectures or whatever you'll find on YouTube. But okay, let's see. I'll assume you know what a differential form is, but other than that, yeah, I'll just give some tools for understanding, tools for computing, and I won't prove in my viatories, but I will use it in the end to, along with a few other things I won't prove for keeping this concise somewhat, to compute the Rham cohomology of the circle. And I challenge you to compute the Rham cohomology of the general for all spheres using induction, because I'll prove the n equals 1 case. Now, this video is on the Rham cohomology. Next time I'll be looking at what happens if we let the space have compact support, so compactly supported de Rham cohomology, or maybe just compactly supported cohomology, we'll see. And some more stuff about the de Rham cohomology, and then after that we're going to be looking at the sheaf cohomology. And then after that I'll go back to normal. Maybe I'll do sheaf theory as a whole series, or maybe I'll just go back to key theory or algebraic, or whatever, basically. Those are the next 3 videos. But enough rambling. I said I was going to keep this concise. I'm going to have an hour-long lecture on my whole YouTube plan before I get into this video. But okay. First off, let a to the p of m denote the... I'm going to say set for simplicity, but it actually is a vector space of smooth p-forms. On M. Now we can have what are called exterior derivatives, if I'm not mistaken, which are maps between these vector spaces of smooth p-forms on M. So these are denoted d to the p, and they take you from a to the p of m to a to the p plus 1 of m. Okay, now they satisfy a crucial property, and that is that d to the p plus d to the p composed with d to the p plus 1 is equal to 0. Okay, this is actually very crucial property, very helpful as well. And, sorry, it should be the other way around. Okay, anyway. Now, say we have a sequence of these. So we have a to the 0 of m, and this will go to d to the 0, to a to the 1 of m, and so on, until we have d to the p minus 1 to a to the p of m, just so that you get the pattern and so on. Now this is a differential complex, and again d to the p plus 1 composed d to the p equals 0. This is where we shall start off. But actually, we can do better. How can we do better? By taking the direct sum of all of these. And actually, well, this is for more general terms. We can just put them all together. But actually, we're going to be studying each individual one. But okay. We can package them together. Actually, it's good to know this so that we can define something important, a very important operator. A star of m is equal to the direct sum for p greater than or equal to 0 of a to the p of m. Now, we have maps between all of these, d. Which is defined as being d to the p at each a to the p of m. Okay, because this ranges all of them. Now, because of this, a decomposed d is equal to 0. Also, it satisfies a Leibniz rule. Okay, so d of omega wedge tau is equal to d omega wedge tau plus -1 to the p omega and then wedge d tau. Okay, so this might look a lot complicated, but actually it's not that different from the product rule you'll learn in calculus, but with this -1 to the p. Remember, this is that p. Okay, now, what more do we have? We have to define what it means for a form to be exact, okay, and closed. So, a p form, omega, is closed if d omega is equal to 0, and exact if there's a p-1 form, tau, let's call it, so that d tau equals omega and tau is in a to the p-1 of m. Now, z to the p of m is the set of all closed forms. Of course, I mean p forms. Sorry, p forms. Okay? And b to the p of m is equal to the set of closed. Sorry, not closed. Exact p forms. And this is obviously a subspace of this because decomposed d is just 0. Now that we have this out of the way, we're ready to define the de Rham cohomology. How is this true? Well, the de Rham cohomology is actually given by a direct sum of the pth de Rham cohomology group, which is what we're going to be studying, and which is much more nice to study with because we can have sequences between them and stuff like this, such as the MASSIVE. De Rham cohomology H star, and then we have a little subscript dr to know that we're working with the de Rham cohomology of m is equal to the direct sum for p greater than or equal to 0 of hp dr. And this is the pth de Rham cohomology group, and this is just a quotient group here. So this is just the pth cohomology group. Like this. Whoa. Okay. Now that we have this definition, we can use some tools in order to compute it. Now, one of them is that, and I'll leave you to show this, it's actually quite easy, it almost follows instantly, is that the de Rham cohomology, the nth de Rham cohomology of a disjoint union of mi's is equal to the direct sum of all of the individual nth de Rham cohomologies. Okay? Now, we shall move to the other side of the board in order to study them more. So here's the MASSIVE sequence. This is going to be very important in computing the de Rham cohomology of the circle. Okay? So, if we have U and V open subsets of a smooth manifold M, such that U union V, so their union is M, then for all n, there is a connecting homomorphism, so this delta is called a connecting homomorphism, and this takes you from the nth de Rham cohomology group of U intersect V to the nth de Rham cohomology group of M, such that, and then we have delta coming into the nth de Rham cohomology group of M, and then this goes via the inclusions below, direct sum, to the nth de Rham cohomology group of U, direct sum the nth de Rham cohomology group of V, and then this goes via the inclusions below to the nth de Rham cohomology group of U intersect V, and then this goes via the connecting homomorphism again to the n plus 1, and so on and so on. Now, our final goal here is to compute the de Rham cohomology of the circle. But first, we'll need some theorems. Okay? Well, let's see. First, we have that the nth order de Rham cohomology of a certain point is equal to, and this is piecewise, it's equal to R if n equals 0, and 0 if n is bigger than or equal to 1. Now, why? Why? Okay, well, actually, it's not too difficult to show. Because if we consider the cochain complex this, okay, so we have 0, and then this will map to A0 of star, and then this will map to A1 of star, and then so on, so on. Actually, this is equal to 0, and then this will map to R, because this is the set of functions, because this is the same thing as C infinity of star, from star to R, and then that's just R. Now this will go to 0, because there are no, because the point is 0 dimension, yeah, the point is not a high enough dimension for this to be non-trivial, and that will hold for the rest. So now we have this. Now taking the cohomology group is leaving us with the following. This is equal to the kernel of the map from R to 0 mod the image of the map from 0 to R, or 0 otherwise. And this is equal to, as conjectured, R for n equal to 0 and 0 for n bigger than or equal to 1. Okay? Now, let's not waste any time. Let's move on. The Poincare lemma generalizes this, and this is making it very, very easy. A contractible space is one which is homotopic to a single point. Now, if M is contractible, then the nth de Rham cohomology group of M is equal to R for n equals 0 and 0 for n bigger than or equal to 1. Okay? Now, if M is compact, sorry, not compact, if M is connected, as the circle is, then the 0th de Rham cohomology group of M is always equal to R. Now, these are just some results I'm going to state without proof, because the proofs are quite short, but I want to kind of fit everything into here, okay? And the proofs are quite short, and I can leave them to you. So now, the final one is, if we have a sequence, a finite exact sequence, not short, just exact sequence. Okay, so it's finite, so we have 0, and then this goes all the way up till, sorry, we'll have one term to A1, and then this goes via, let's say, D1 to A2, and then so on and so on. And then this goes via D, and then this goes via DP to AP, like so. Sorry, this goes via DP minus 1 to AP, like so. Then the sum from I equals 1 to P of negative 1 to the I times the dimension of A to the I is equal to 0. Okay. Now we're equipped with the tools we need. Okay, so I conjectured that the first, actually we'll do this piecewise. The nth de Rham cohomology group of the circle is equal to R for n equal to 0 or 1, or 0 for n bigger than or equal to 2. Okay, for n equals 0, well, it's connected, so it's true. So actually we just need to compute it for 1, because it's because of course when the dimension is bigger, the n here is bigger than the dimension, it's going to be trivial because there are no n forms on a bigger dimension. Now, how should we do this? Well, actually we're going to use Viatores. But what we're going to pick U and V. U is equal to the 1 sphere minus n, where this is the North Pole, and V is equal to the 1 sphere minus the South Pole. Now, of course, their union is going to be the 1 sphere, and, yeah, okay. Wait, their union is going to be... Yeah, their union is going to be the 1 sphere. Yeah, sorry, I'm overthinking this. Yeah, the union is going to be the 1 sphere. Okay, now, there exists a delta so that the following sequence is exact. Now remember, this can be finite, and we're going to use it to be finite. Because if we go up in higher dimensions, every term is just going to go to 0, so there's no point really. So, we're going to have 0, and then this maps onto the 0th de Rham cohomology group of the circle, as is here. And then this will map onto the 0th de Rham cohomology group of U, direct sum by the Viatores of V, and then this is going to go to their intersection, the nth de Rham cohomology group of their intersection. And now, this is going to go by the Viatores precisely to the thing that we want. The first de Rham cohomology group of the circle. Okay, and now this is going to go again to the first de Rham cohomology group of U. Direct sum the first de Rham cohomology group of V. And then this is going to go to the intersection of the first de Rham cohomology group, and then this we're going to take to 0. Now, this is exact, and with these tools we can clean it up a lot. We're going to have 0, and then this is going to be R, and then this is going to be the direct sum of R and R by this, the Poincaré lemma. And then this is going to be going on to, well, this is smoothly homotopic to a 2-point space. So actually, by a theorem that I didn't write down, it's actually just going to be the direct sum of r and r. And now this is what we want. So we're just going to leave it as it is because we don't know what it is yet. And now this, because they're contractible and n is bigger than 1, it's going to be 0 direct sum 0, which is 0. And similar reasoning, we're going to have 0, 0, 0, and so on. I'm just going to have another 0 for safekeeping. Okay. Now this is a finite exact sequence. So we can apply this theorem. Well, what's the dimension of 0? 0. What's the dimension of r? 1. Plus. Sorry, alternating signs. We're going to have minus. What's the dimension of this? 2. What's the dimension of this? 2. What's the dimension of this? We don't know. That if we find this out, then we'll be able to do it. If it's 1, for example, then our conjecture will be correct. And then the rest is 0. And this is equal to 0. And by simple algebra, these two cancel. Add this on both sides. The dimension of the first de Rham cohomology group of the circle is 1. Therefore, the de Rham cohomology group of the circle is R. Okay. That was nice. We use these tools with these prerequisites in order to not prove, but I did state a few theorems. This one was proven. This one was proven. This you use telescoping sums. This you just plug in the definition actually, straight from this definition. And this you use this. So this one is the easiest. This one is hard. You use something called the zigzag lemma, which you can look up in your own time. And yeah, that's going to be it for today. Hopefully this was a good explanation. I really want to get this video correct. I mean, not correct, like the explanation good. So yeah, I really hope that you found this helpful. And I'll see you in the next video. Bye.